Yeah, welcome to the second session. After food, I think so we should get back to the talk. So first talk in this session will be by Takahiro, and he's going to precursory acceleration before breakdown. This is related to the earthquake.
Yes.
Okay. Yeah. So.
Thank you. Organizers for giving me this opportunity to participate in this wonderful conference. And I'm working on a kind of geophysical phenomena, and we'll talk about this issue from the viewpoint of statistical physics. And most of the work is done in collaboration with Dr. Spadip Roy, who just moved to BITS Pirani in Hyderabad. So in geophysical situation, there are many natural disasters ranging from landslides and volcanic eruptions and also earthquakes. And these three are just the natural disasters, but sometimes this kind of large building may collapse spontaneously. And this can also cause a very serious disaster. And both of them involve a kind of slow and time-dependent deformation process that leads to failure. And that is the main concern here. So what is very difficult about earthquakes or the material failure is that we cannot see inside, so we can obtain a very limited information about what is going on in the system. In contrast, both Japan and India suffer from typhoon or cyclones. In this case, we can actually see what is going on by the information obtained from satellites. So in such cases, time evolution is known because we know the underlying physics, which may be Navier-Stokes equation. So we know much about this kind of system. But for this kind of solid Earth or more complex materials, the basic physics is basically not known, and they mostly involve rheological problems. And also that can be also combined with the problem of phase transitions. And it makes the problem very complicated. So of course, we know the continuum mechanics for this kind of solids, but main problem is that we don't know the constitutive laws that governs deformation of solid Earth. And due to this information loss, sometimes earthquakes are very abrupt, as well as volcanic eruptions and landslides. They are mostly occur suddenly. So the natural question would be, are these kind of natural disasters intrinsically abrupt? Or it is just because we cannot observe their signs due to the difficulty in observations. So this is a kind of hypothetical questions, but we can ask in such a way: are they, would they be predictable if we could obtain all the necessary information? in different words, we can also say like this. Are they predictable in laboratory where we can obtain all the necessary information? So, of course, the observation is a very important problem, but here we don't consider this and separate the problems between the physical mechanism and also the difficulty in observations. So we focus here the essential mechanisms that lead to sudden catastrophic events. So in case you are not familiar with solid failure, this is just a brief review of the theory proposed by Griffiths, which is more than 100 years ago. So this theory consists of two ingredients in the mechanical energy stored in the solid objects. The one component is the elastic energy decreases due to the increase in the length of the cracks. So suppose this object contains the size R pre-existing crack, and with this size R, the total elastic energy stored in this object decreases like this. Here is the Young's modulus, and sigma is the applied stress. And the other component is the interface energy and crack. And this is proportional to the size of the crack. And the proportionality coefficient is gamma, which is the surface energy of the solid. By considering these two components, the total mechanical energy of solids as a function of R looks like this. So first, it is an increasing function, so we need work to extend this graph. But if the size exceeds some threshold, which is denoted by RC, then the total energy starts to decrease as R increases. And that means we don't need force to extend this crack. And that means the material instantaneously fails. And this Griffiths criterion can give us the hint to estimate the distance to the failure. We can have this RC as a function of the applied stress and also the surface energy. So, and also we know sigma, and from this we can infer this RC. And also we can consider like this. So, suppose we know the maximum crack size that is contained in a specific sample, and that is R max. And if we know R max, then from this equation, we know the threshold stress, sigma. And if the applied stress is larger than this value, then the sample will break. And this is given by this kind of equation. So in this simple theory, one can basically know the critical stress or the failure stress of object. But it is basically very difficult to know the size of the pre-existing cracks, and that would be a difficulty in observations. And to know such a size is very difficult, and also the more difficult point in reality is that solid material is very heterogeneous in usual. It is, of course, in the case of landslides or any geophysical situation, but also man-made structure has a lot of heterogeneous structure that make material more strong. So in this case, this surface energy gamma, or this Young's modulus E, can be also heterogeneous, which makes the problem more complicated. So in such cases, simple Griffith theory doesn't apply. And also, in addition to the heterogeneity, this kind of inelastic process is also very important. And for complex materials, damage accumulation process occurs if we deform such objects. And that can be understood as the increase of the density of microfracture that degrades the material. And as the number of microfracture increases, the system eventually fails. And in this case, stress-strain relation becomes much more complex than this kind of ideal brittle materials. And what I'm going to talk about in this talk is that this stress-strain relation becomes time-dependent due to the microfracture or micro damage in the solid materials. So this is a schematic picture of the deformation process, I mean the time-dependent process. So the point here is that stress is time-independent. So here the applied stress is constant, but the deformation of the materials occurs at this constant stress. And this is how the strain looks like as a function of time. And after the application of constant stress, the system deforms, and the strain rate is large at the primary stage. And then this is followed by the secondary stage, or secondary creep, in which the strain rate is almost constant. And then after sufficiently long time, this strain rate again accelerates. And this acceleration leads to the failure of the system. And this acceleration behavior is called tertiary creep. And what is important here is the first stage, the primary creep, which is described by the power law. as a function of time with some exponent alpha. And the third stage, the tertiary creep, is also described by the power law with exponent alpha prime. And this alpha and alpha prime are basically different thing. And here, TF is the failure time of a specimen. So following this equation, the strain rate goes up to infinity towards the rupture. So if we know this tertiary creep.
I have one question. So the secondary creep, why are you saying it's constant? I mean, this is a confusion because typically when we have steady flow, at that time we also say that epsilon dot is constant. Right? So
Yes.
therefore, are you expect that it's not constant but has some time dependence in the secondary creep?
I'm not sure. So this is a very, how can I say, schematic scenario leading to failure. So with very fine observations, we can actually see a subtle time dependence in the secondary creep. But here we don't consider this. Thank you. So if we are interested in the failure time, which may be the time of the catastrophic failure, then this can be used for forecasting the failure. And also, this kind of power law acceleration is common to earthquakes, not only in materials science, but is much larger scale. And this states the aftershocks occurrence rate decreases as a function of time. And here the time is after the main shock, measured after the main shock. And here C is the time constant, which may depend on main shock. And also this exponent P appears, just like in this case. And if we have if we focus long time behavior in which the time is sufficiently larger than this time constant, then this n dot is just power law with this exponent P. And that is comparable to the primary creep with this. But these exponents are basically different things, because here alpha depends on the deformation rate or strain rate, but here P or the exponent P involves n dot, and here n is the number or the rate of the acoustic events or seismic events, which are aftershocks. So basically, this P and alpha could be different. And on top of this exponent and the similarity to primary creep, here this time constant C is also important in the context of earthquakes, because it is insisted that this C is a decreasing function of shear stress acting on the fault zone. So suppose we have an intermediate size of earthquakes and aftershocks follow. Then we measure aftershocks rate and fit the data with this law. Then we can infer C. And if C is large, then the entire stress acting on that area is still low. So we are not in danger in having more earthquakes. But if we observe a smaller sea, then the shear stress on that area is still large. So there could be more risk to have further earthquakes. But shear stress acting on earthquake fault is, of course, not directly measurable because it is very, very deep, like 10 kilometers or to 20 or 30 kilometers. So this is still at speculation. But in laboratory experiments or computer simulation using a simple model for rocks, some people have confirmed that this C is actually a decreasing function of shear stress. So this is also one of the focus here. And probably the most useful thing that could forecast large earthquake could be this inverse Omori law that corresponds to tertiary creep. But unfortunately, this kind of Omori law that leads to major earthquake has not been observed in natural earthquakes, whereas it is always observed in laboratory experiments. So it's a kind of a very big issue in seismology. But what is interesting is that in landslides, this kind of acceleration behavior is commonly observed before we observe large-scale landslides. So after heavy rain, we can deploy geodetic measurement in the sites that are at the risk of landslide, so people can observe the real-time deformation before landslides. And in most cases, we can observe this kind of behavior. And here, V is just the speed of the deformation of the surface. And in this case, P prime is mostly more or less 1, but sometimes large. And last example from a geological scale is volcanic earthquakes just before the eruption. And before eruption of volcanoes, there are many earthquakes observed in the body of the volcanoes. And this is because volume inflation of volcanoes due to the rising magma. And this is one example taken from this paper. And this is the rate of volcanic earthquakes as a function of a day. So this is November, and this is starting from November 1st. And the volcanic eruption was on 15th, and the rate of volcanic earthquakes increases towards this 15th. So, so far we have reviewed the common phenomenology between earthquakes and landslides and also volcanic eruptions. And these share the common properties like this. So here we would like to put forth these questions. What determines this exponent alpha prime and also p prime, which usually ranges from 0.6 to 1.5 or something. And if we can know this exponent beforehand, then it can be used as forecasting the time of failure. And also, in the context of Omori law, this time constant is important as it may the indicator of the shear stress on fault zone. So to know this kind of problem together with physical mechanisms, we need a model study. So the model we use here is extremely simple, which may be sometimes called a fiber bundle model. So here we discretize the solid into n finite elements. And if a force is applied to this specimen, then this n discrete elements will support the load equally. So this Fi denotes the force acting on element, or I. Then the summation taken for these entire elements should equal to large F. And to model the randomness contained in actual materials, we introduce own fracture strengths for each element. And this is denoted by HK for element K. And this HK is chosen randomly from a certain distribution. And this threshold probability distribution could be arbitrary. That could be a Weibull distribution or any other extreme value statistics. And also we can consider the randomness in elasticity, but it is eventually incorporated in the randomness of the fracture strengths. And to consider the dynamics, we need to consider the force relaxation process or stress relaxation process. During the stress redistribution process, this relation should be observed. So if some fibers or some elements are destroyed, then this end decreases, which means that force per element, force per surviving element should increase. So with this mechanism, if some fiber is broken, then more fiber will be broken. And that is a kind of chain reaction that leading to the failure of the entire system. And so generally such a force distribution or stress redistribution has a very complicated manner following the theory of elasticity. But here we focus on a very simple model, which is a mean field, where this force per element is the same for all the surviving fibers. And also we can consider time evolution like this. So the first step is force per element is given. And yeah, okay.
The fibers cannot grow back, right? That is what you're
no, they cannot. Thank you. So some elements break if the threshold is exceeded with this Ft. And then after some elements are destroyed, then force per fiber is recalculated. And this defines the force per fiber at the next moment. And with this kind of loop, I mean, time evolution loop, one can write down the very simple equation, which is the fraction of surviving fibers at time I plus I is given by the force per fiber at time I. And this P of H is a threshold distribution. And using this relation between the force per fiber and surviving elements, and then we can write the time evolution equation for F, which is the force per elements. And in actual physical process, this kind of rupture of fibers and stress redistribution takes some time. And this time scale can be regarded as an intrinsic time scale in this model. So by introducing this time scale T, this is considered as the time derivative of the force per elements. So we can have ODE for the force per fiber. And this F dot is also proportional to the strain rate, since the strain is proportional to the force per fiber. So we can also think that this is the time evolution equation for the force per fiber, or the strain rate. And because the model is so simple, one can get the analytical solution for a specific uniform distribution case. Here, the maximum value for the threshold is denoted by Fmax, and width of the distribution is delta. So the actual distribution function is written like this. And with this, one can rewrite the time evolution equation using this P of H, and can end up with this non-dimensionalized time evolution equation. Here X is the non-dimensional force per fiber, and this zeta is the non-dimensional load, which depends on F naught. And here the important parameter is zeta here. And if zeta is small or is negative, there exist two fixed points for this time evolution. And the smaller one is a stable fixed point, and the larger one is unstable one. And for zeta vanishes, the saddle node bifurcation occurs because this term will vanish. So the stable fixed point and the unstable fixed point merge. And for positive zeta, there are no fixed point, which means that this X monotonically increase with time, which means that the system will eventually fails. And for zeta is larger than 0, when the system undergoes failure, one can solve this time evolution equation to obtain this kind of form. So this T is the time, and here X is the non-dimensional force. And this expression is further simplified if the force is not very large. Then we can write this solution like X equals to this equation. And this equation leads to also the power law for the first stage of the deformation, and also the accelerating behavior at the later stage with exponent -2. And also we obtained analytical expression for the time constant C. So with this, we can reproduce the power law behavior for these two stages of deformation. And here we did it for the uniform distribution, but we can show that this scenario is valid for more general stress redistribution like this. For this, we can, it is easier to go back to this recursive relation. And here, phi is defined using the threshold distribution. And since this is a map from Fi to Fi plus 1, one can consider the time evolution in the space of Fi and Fi plus 1. And one can write the function phi in a solid line, and also Fi equals Fi plus 1 is a dashed line. So the intersection defines the fixed points. So since this phi is a function of F naught, which is the initial force, if F naught is small, then the entire shape of phi is at the lower place. So we have two fixed points. And one can easily see that this is the stable fixed point, and this is the unstable fixed point. And for larger initial stress, this phi of F goes up, and eventually these two fixed points merge together, forming one single unstable fixed point, which is a saddle node bifurcation. And even if this F node is slightly larger than this F node, we can expand this phi of F around this FC. And with this expansion, one can obtain the time evolution equation F node, and we retain the power law behavior with the exponent 2. And this power law behavior with the exponent 2 is a general property resulting from the saddle node bifurcation. So this is just a numerical demonstration. Here we confirm the Weber distribution, and we also confirm the power law behavior with the exponent 2. And of course, this is a very simple model, so it is not surprising that we cannot reproduce the exponent, which is comparable to natural observations, which ranges from 0.6 to 1, while it is 2 in the model. And also, what is not happy is that this time constant C is an increasing function of the applied stress, which is opposite tendency as proposed in the numerical simulation or earthquakes observations. So to consider some more possibility, we extend the model in which each fiber can break stochastically. Okay. And this is described by this kind of thermal activation process like failure rule. And we can write down the time evolution equation for the distribution of the surviving fibers. And we retain the power of behavior with exponent comparable to observations. But unfortunately, this exponent matches the value for natural observations, but it depends on the detail of the model. And here, also by incorporating this stochastic rule, one can see that this C is actually a decreasing function of the shear stress. So we don't have time, so we skip the last part. And this is a conclusion. So due to the simplicity of the model, we obtained analytical solution for the time evolution of the deformation rate, and then find a robust exponent 2, which is a result from saddle node bifurcation. Here. And also the time constant C can be either increasing function of stressing, decreasing function of the stress. And so this C would be based on more subtle physical mechanisms. And that's it. Thank you very much for your attention.
We have time for questions, and yeah, list Pinaki.
Yeah, Takahiro, you skipped over the self-healing part. Can you just go over that?
Thank you. Thank you for that. So healing process is very important in snow failure or ice or granular matter. So on top of the stochastic fracture rule, we also incorporate the healing process with a stochastic rule. And the healing probability is just proportional to the number of broken elements. And this means that we assume that the healing is a two-body process. Broken ones and two broken ones meet up. And with this we can write down the time evolution equation. And
There's no time scale for the healing source.
That's a good question. Yeah, there is a time scale. There should be a time scale for healing, but here we consider it is the same for the stress redistribution. Obviously, it should be much longer, maybe. So, but here we assume the same time constant. And what is interesting that we observe the acceleration behavior with the exponent -1. And what is interesting is that relaxation process after we apply constant stress. And this is a strain rate as a function of time. And depending on the healing rate, if the healing is large enough, then it eventually goes to steady state. But the healing is not sufficient, then the system will fail. That corresponds to the increase in this branch. And what is interesting is that these behaviors can obey the scaling law, just as we observe for particulate system near jamming behavior. And also this exponent t to the half is also common to particulate systems.
Santan, you have a question?
Yeah. Yes. So you mentioned about how the event rates in earthquake it decreases with time. So the size of the event, does it have a dependence?
That's a very good question, because it has been also a matter of discussion in seismology. And some people believe that average size of earthquakes is not time dependent, even in the aftershock regime, but some people insist that we tend to have larger aftershocks right after the main shock, and average size will decrease as time goes on after the main shock. So we don't have a particular answer for that question for the moment.
Okay, thanks.
One more question? You have a question? Yeah? No. Okay, so you raised. Yeah, if there is no further question, then let's thank Takahiro for this nice and interesting talk.
Thank you very much.
So we move on to our the next session, which is flash talks by all the poster contributors. And I'm going to read names of individual ones. And unfortunately, you have only 1 minute to talk about your work and then tell many. So tell the audience to attend your posters. And okay, so first one is by Nishant Birdi. Yes, so maybe some of you can stand one by one.
Giving flash talks, just come ahead.
But maybe, Nishant, here, you go up. Then
Good afternoon, everyone. So, for today's for this poster presentation of this conference, my topic is equilibrium phases and growth kinetics of calamatic liquid crystals, where we are going to discuss about the phases that are there in liquid crystals, the nematic and the smectic phases, which are not completely solids or liquids, but in an intermediate state, and how the transitions take place, how the energy anisotropies in these phases affect the phase transitions and their kinetics, how the growth ordering evolves. So we'll discuss all that, and you can attend my poster round. So there I'll explain everything.
Hello, I'm Shakul. So in my poster, I'm going to discuss about oscillating states of driven Langevin systems under large viscous drive. So the models that we study are Markov stochastic processes, which follow a specific Fokker-Planck equation. And this Fokker-Planck operator in the first equation is time periodic. So it's explicitly time dependent. And as a prototypical example, we take a driven Brownian particle in which not only the force is time periodic, but also the noise strength and the coefficient of viscosity. And these large time distributions of such systems we call oscillating states. They are independent of any initial condition from which you evolve the system. But in this particular presentation, the poster presentation, I talk about for a fixed thermal drive, what happens if we change the viscosity.
Yeah, but I think it's okay.
Hey, welcome back to the last session of the day. And this session, there are 3 talks. First talk will be by Ayon Santra, talking about activity-driven transport in harmonic chains. And you have 20 minutes, okay? So at around 15.
So the 20 minutes full or it's 15 plus 5?
15
Okay.
plus 5, yes.
Yeah, okay. So first of all, I would like to thank the organizers for giving me this opportunity to present some of the recent work that I have been doing. And so yes, today I'll talk about activity-driven transport in harmonic systems, which is a joint work done with Urna Basu from Shoten Bose Center, Kolkata. And it will basically be on these 2 papers. It will mostly be on the first paper, and I'll briefly mention about the second one. Okay, so let's begin with transport. So transport in particular is something which is known to us all, thermal transport, or more in particular thermal conduction, heat conduction. So I mean, people have been interested in heat conduction problems for a long time. So the basic picture is like you have a hot reservoir and a cold reservoir, and you connect it with some conductor, like a conducting wire or something, and then people are basically interested in the energy current, heat current that flows from the hotter reservoir to the colder reservoir, and what is the temperature profile along the length of this conductor, and so on. So there are many empirical laws, like Fourier's law is one of such laws which which tells you how this conduction happens and what is the current and so on. So theoretical understanding of these energy transport basically considers a Hamiltonian system which is connected to basically thermal reservoirs, which are, for example, Langevin baths, which are like equilibrium reservoirs with satisfying fluctuation dissipation theorem throughout. Okay, so the first analytical work in this regard was done in 1967 by Reidel, Lieb, and Lebowitz, where they considered a very simple system, an ordered harmonic chain connected to 2 Langevin baths at the 2 ends. So the Langevin baths are basically modeled by a constant dissipation and a fluctuating part, and a fluctuating noise, which is the Gaussian white noise, where the strength is actually proportional, related to the strength of the dissipation. So what you see here is basically this is the harmonic chain, and the 2 ends are connected to the baths, which are modeled by this red and blue parts, and the remainder of the chain is completely Hamiltonian, and they follow Newton's equations of motion. So what they found in this paper was that the average stationary current actually survives in the thermodynamic limit, and it's proportional to the temperature difference of the 2 thermal reservoirs, and the kinetic energy, average kinetic energy of each oscillator in the chain, that gives you the local temperature. And the average kinetic, if you look at the average kinetic temperature profile throughout the length of the conductor, you find that it's flat at the bulk, and it's just given by the arithmetic mean of the reservoir temperatures. These are all quite contrary to what is predicted from Fourier's law. And over the years, many generalizations of this model has been studied with pinning in the bulk, disorder, and harmonicity in the chain, and so on. But most of the studies in this respect has been with equilibrium reservoirs. So the forces that are there at that the bath end exerts on the end particles always satisfy fluctuation dissipation theorem. So now the question I'm going to ask today is, what happens if these reservoirs are out of equilibrium? And when I talk of out of equilibrium, so active particles have emerged as a paradigmatic example of out of equilibrium systems in the recent years. So active particle has already been introduced in the talk by Shraddha Mishra today morning. So they are basically self-propelled particles like bacteria, genus beads, and Zener beads which can dissipate and generate persistent motion. They're out of equilibrium and they violate fluctuation dissipation theorem even at the single particle level. So advanced microrheology experiments in the recent years have allowed people to study the effects of a probe particle. If you put a probe particle in a bacterial or in a living medium, then what happens? What is the effective dynamics of this probe particle? So a lot of experimental and numerical activities have been carried out in this regard in the last 1 decade and so on. And unusual properties like negative friction, modification of equipartition theorem, and anomalous relaxation dynamics have been seen. So now again I modify my question further. I will ask what happens to the transport properties of an extended system when it is connected to 2 active reservoirs. So this is kind of a pictorial representation of what I'm going to discuss. So the first thing when I want to study this would be how would you, so thermal reservoirs were modeled, coupling to the thermal reservoirs were modeled by forces which followed fluctuation dissipation theorem. So how would you model the coupling to an active reservoir? So this is a simple model which was studied in this paper where you take an kind of independent oscillator model. So you have a test probe particle in between, which is this red one, and it is connected by harmonic springs to these black particles which follow overdamped active particle dynamics. So I model this active particle dynamics by just an exponentially correlated random noise, which is followed by the generic active particle models that you find, like run and tumble active Brownian particle or direction reversing active Brownian particle. So because of the linearity of these equations, you can integrate out the degrees of freedom of the bath, which is y, and then you can write down an effective equation of motion for the red particle, which is the tracer. So it turns out that the equation for the red particle is a generalized Langevin equation, where this is the memory kernel and this is the effective noise that is experienced by the red particle, which have these following forms. And if I take the strong coupling limit of this, so that is this coupling strength is much larger than the other parameters, so then basically it reduces to a Langevin equation, a normal Langevin equation with constant dissipation and an effective noise. So the takeaway from this is you can model the coupling to an active reservoir in the strong coupling limit by just adding a force which is related to the individual correlations. The correlations of this force and the constituent active particles of the medium are basically the same. And this also has been taken as a model in in the previous experimental studies done in the past. Okay, so now we come to the model to study the activity-driven transport. So it is essentially the same model as the Ryder-Lieb and Lebowitz model. But now we have, other than this, the part coming from the thermal reservoirs, we have these additional forces F1 and Fn, which are exponentially correlated. And this tau j's, so tau 1 and tau n, basically, these give you the measure of these are basically the characteristic time scales, or the activity time scales, which basically is a measure of the activity of the system. So higher the tau j is, higher the activity of the reservoir. And again, the bulk oscillators follow Newtonian dynamics. And yes, so the system, because it's connected to two reservoirs, in the long time limit, if you look at it, it will reach a stationary state. And we are interested in this talk, especially I'll talk about the current that flows through the system in the stationary state and the average kinetic temperature profile of the conductor chain in the stationary state. Okay, so let's come to the results directly. So the average current that flows through the system, because it's a linear chain, it turns out that the average current that flows through the system separates out into a thermal part and an active part. The thermal part is exactly same, proportional to the temperature difference as in the RLL model. So I'll just take them to be 0 in this for the following discussion. So if I look at the active current, what you see is it begins from negative, it crosses 0, it becomes positive, hits a maxima, again changes sign, and then goes again to some constant value. So we actually can get an exact expression for the current in the thermodynamic limit of the chain, which is something like this. And so this non-monotonic behavior of the current is basically, so the x-axis of this is the activity drive. So basically what I do, I fix the activity of one of the reservoirs and I increase the activity of the other. So basically this, it's some kind of a tau 1 minus tau n if you consider that way. And this negative difference, so in one regime what you have is actually when it's decreasing, so what you have is you're kind of increasing the drive and the current is decreasing, which is quite counterintuitive. So this negative differential conductivity is actually a signature of non-equilibrium dynamics. It has been previously seen in systems with nonlinear models and with models where there are different kinetic constraints. These are a few examples, but interestingly, the presence of active reservoirs causes this negative differential conductivity to occur in a linear chain. And I don't know. So basically, if we look at we've tried to look for some physical origin, but we were quite unable to find something. But what we can say is like this is some intermediate step in the calculation where we get some kind of an active Landauer formula where the system or the transmission coefficient, which is given by this basically your current is an overlap between this transmission coefficient and the reservoir frequency spectrum, which is nothing but the Fourier transform of the exponentially decaying autocorrelation. So the system spectra is basically peaked at the characteristic frequencies, which is proportional to the spring constants of the harmonic chain, while the reservoir spectra is a Lorentzian, which is peaked about the origin. And if you look at the overlap of them, you find that actually is non-monotonic. If you look at this plot carefully, so that is non-monotonic. So that actually contributes to the non-monotonicity of the current. And there's another interesting thing that happens in the current is it changes its direction twice. So what you expect is normally is like if you give a drive and then the current would be zero when the drive becomes zero. So there is one zero where the current is zero once when the drive is zero, but additionally there is another point denoted by these red dots where the current is zero. So there is this additional directional reversal. So if you look at the phase space of the phase diagram of the current in the activity plane, so you would see this diagonal is basically giving you the trivial zero when the activity drive is zero, and then this red solid line basically gives you the non-trivial zero, where the activity drive is not zero but the current is zero. And the intersection of these 2 points is, if you just look at a straight line along this, passing through this point, along this or this axis is a particular point where there is no reversal. So basically it hits the zero line and comes back. So that also turns out to be a saddle point if you look at it in 3D. Yes, so now let's coming to the average kinetic temperature. So why are we looking at the kinetic temperature? So basically in equilibrium case, kinetic temperature calculating kinetic temperature would mean that you are calculating it gives you the local temperature at each site. So it turns out again that similar to the thermal case, the bulk profile is flat. However, there is a non-flat boundary layer which decays exponentially. Interestingly, the profile is not completely flat even when the activities are same. And the bulk profile can be calculated exactly in the thermodynamic limit, and it turns out it can be written in this form, which is the arithmetic mean of these two quantities, curly T1 and curly Tn, where curly T is given by this expression. So if you remember the expression for the average kinetic energy for the thermal case, it looked similar with this in place of this curly T's, it was the temperature at the two ends of the reservoirs. And this makes us ask the question that can we now have an effective thermal description for the chain, for this transport, where we can replace the active reservoirs by thermal reservoirs with these temperatures. So it turns out that that description is not consistent, because even if the activities are same, then the thing which we want to call some effective temperature, they are also same, but in that case, still the profile is not completely flat, which is kind of a violation of the 0th law of thermodynamics, because if the temperatures at the two ends are same, then it should be flat always throughout. So that's one check that does not satisfy, and of course, if you take the expression of the thermal current and you put this curly T1 and curly Tn, and then you see that the solid lines are basically the active actual currents, and the dashed lines are the active currents which we get by using this effective temperature description. So in general, you see that they don't quite match, but at very small temperatures, at very small activity parameters, you find that there is overlap, which basically this again follows from the exponential nature of the noise. Oh, that's a long time. Yeah, I'm almost done. So, basically, if the characteristic time scales are very small, so the exponential correlation in that limit basically reduces to kind of some delta function correlation. So this is again that same passive limit where actually an effective thermal temperature emerges. So I think that's all. So yes, so this is the summary. Basically, I studied energy transport. So this is all what I said. The important part from this is the results that I showed, the energy current and the temperature profile. So these results are robust for all kinds of active dynamics. So if I choose my active particle bath to be a run-and-tumble particle or an active Brownian particle or anything, those results are robust. And so the current and the temperature profile all follow that same behavior. And yes, but of course you would see the effect of the exact dynamics, and that is seen in the higher order fluctuations. So this is also, we have calculated them in this paper which was out very recently again. And we can further explore this by putting, I mean, all the studies that has been done in heat transport, like putting disorder and anharmonicity in the chain and etc. everything. Yeah, so that's it. Thank you.
We have a couple of minutes for questions. Yes, Pavan.
You have an asymmetric kind of heat connection across this particular channel. For example, let's say you have some kind of a one-dimensional conduit.
One-dimensional?
Conduit, or some kind of a one-dimensional channel through which you would want to actually communicate between these two parts. If there is an asymmetry between these two parts, would that still be kind of valid to look into such kind of arguments?
By asymmetry, you mean what?
For example, one particular part is at a very high temperature compared to the other one, which is also at a higher temperature compared to the first one. And
this will still, I mean, by temperature you mean the real temperature, or?
Yeah.
Yeah, I think this will still, so it will still work, because the model which says, I mean, you can just put the temperature in, the temperature is basically in the strength of these zetas, xis.
Yeah, is there something which also is dissipative on either side of the walls? That is what I am just...
So the dissipation is basically here, so
yes.
that's all. I mean, you can have any temperature.
You can represent, because there's also a dissipation through the chain, right? Through the...
There's no dissipation in the chain?
In the chain, okay.
Yeah, it's completely energy conserving.
But is that realistic, so to speak? Because there will be some kind of dissipation, right?
No, I mean, then, I mean, yeah, there can be dissipation. You can just model it by some momentum.
You just add one more.
Yeah, I mean, inside in this one, yeah.
Thanks.
I have a question.
Yeah.
So there are some recent studies, also exact calculation for Ornstein-Uhlenbeck process in active scenario, and there the physics can be described by an effective temperature description. And let's say if you have to basically, is there a physical understanding of why it fails here?
No, there's, I mean, Ornstein-Uhlenbeck processes are a bit special. So I'll just show you one quick thing. So when we looked at the higher point fluctuations, so the velocity distribution, if you look at to characterize if it's equilibrium or not, you would see that the velocity distribution of the Ornstein, if the bath particles are Ornstein-Uhlenbeck, it's always Gaussian. It's always the Gaussian, and it's always like Maxwellian. So.
So that
AOUP,
that's-
I mean,
that
yeah,
helps
that's
it.
special because AOUP is anyway you model by some Gaussian noise. I mean, it's one order more, but it's still Gaussian noise. So I think that's why it's AOUP is somewhat special.
So,
Yeah, Madan, yes.
yeah, I didn't understand why, you had 2 zeros of the current, no? And you said 1
Yeah, there's
zero.
no physical explanation why that is, but it's just like that. Yeah. Yeah. So this is RRI where I come from, and this is like the Van Gogh form of RRI. Yeah. Okay.
Okay, thanks for this nice talk, and then let's rank him. The next talk is by Yuval Seher from Tel Aviv University, and he's going to talk about unified approach to gated reactions.
How did he do it?
Just connected to computer.
But it's not full screen. Okay. Okay, so first let me thank Arnab and Pinaki and Arnab students for the hospitality in the last week. I'm Yuval from the School of Chemistry in Tel Aviv, and today I'll be talking about gating, which is my main PhD endeavor in the last few years, gated reactions, or in more generality, gated first passage processes. And my main objective here today is to introduce you to this concept, which is maybe not really known in this community, and give you a tool to explore these processes, to explore gated problems very easily, actually. So I will begin with a motivation from the perspective of a chemist, which is a simple reaction. The most basic model that we can think of would be the Smoluchowski type reaction, diffusion controlled reaction, where we put one of the particles in the origin of our coordinate system, and we let the other react and diffuse relative to it, and we say that reaction occurs on contact. And in more modern terminology, if we look at the mean reaction time, this is the quantity that we are interested in, so simply the mean reaction time will be the mean first passage of that particle to the origin. But as I said, this is a relatively simplistic model, and the next step, a few decades later, was introduced by Collins and Kimball, where they have considered partial reactivity. So now every time that the two particles collide, there's a certain probability of reaction and a certain probability to not react, and we will denote the probability to be reactive on collision by R. So let us calculate the mean reaction time for this model. It's actually a very simple calculation. The first term remains. The particle, of course, still need to meet for the first time. But now what would be the additional contribution? So after they meet, we ask the question, did the particle react or not? If they did not react, they need to meet again. Now this is not a first passage process, it's a first return process. And after this first return, after they return, we ask the question again, did they react or not? And we do it again and again. Essentially, this is just a sequence of trials, geometrically distributed, with this probability by R to react, and we know the number of attempts is just 1 over this probability. That will be the mean of this distribution. Each trial will take on average the mean time that it takes it to return, and the contribution will just be that. So I'm claiming that this is still relatively simplistic, at least at certain cases, because here we neglect correlation, and by that I mean by assuming that every time that the two particles collide, we are neglecting correlation between the internal dynamics of the particle, of the system, if such internal dynamics exist, and the spatial process and the return process. And that is essentially where the theory of gating is needed. And maybe to illustrate that point even further, here is a cartoon. So let's say that the particles collided and did not react. So we know that the system is in the non-reactive state, where the two particles are at distance 0. Now consider two different trajectories possible. One of them is very short, and one of them is a very long trajectory. So if I was non-reactive to begin with, you might expect that after a very short trajectory, I have higher probability to still be non-reactive versus a very long trajectory where the internal dynamics have enough time to equilibrate. And that is exactly the correlations that we talked about. And why we call it gating, because in biology and in chemistry we imagine an entity such as a ligand or an enzyme that has a part that acts like a gate that opens and closes, and only in the open conformation it can admit the ligand. But for the remainder of this talk, let us make it more abstract. We have just two states, a Markov chain, a reactive state and a non-reactive state. And it actually doesn't have to be a chemical reaction. It can be any first passage process and any set of constraints. We call the set of constraints, if they are fulfilled, we are in the reactive state. If they are not fulfilled, we are in the non-reactive state. And just an historical comment, the theory of gated reactions in the macroscopic case at least is studied from the 80s by McCammon, Shop, Szabo, many other people, and it's actually is getting renewed attention in the last years, where people mainly deal now with the microscopic single particle problem. But there are a lot of works, and when me and Shlomi Reuveni from Tel Aviv considered the problem, we didn't want to just solve a specific case. We want to build a tool to study this kind of reactions. And we started with CTRW, continuous time random walks. So we are in continuous time discrete space. And these are the rules of the game, essentially, that we are postulating. You can have any network, means any dimension, any connectivity, and any spatial dynamics on that network. It means that the waiting time in each site doesn't have to be exponential. And also, of course, it can be non-homogeneous. Every site can have different waiting time. The only thing that matters here is that once we set the rules, they do not change with time. So on every iteration, if the particles did not react and they need to meet again, the network is not changing in time. So that is a complete generality except that. And we now divide and rule. We start by looking at the internal dynamic system, which is simple. And we define the relaxation time of the system and the equilibrium occupancies, pi r and pi r for being reactive and pi not reactive. And the only quantities that are of interest of us, they are sort of the internal dynamics propagators, or just the conditional probabilities. If you started in the beginning in the non-reactive state, after time t, what is the probability that you will be reactive or non-reactive? All of these four combinations. So once we have this, we are good to go. And we now tailor it with the spatial process. So how do we do it? So let's say the particle started at a certain location, R0, in a certain state Q0. The first leg is actually simply a first passage. So we all know it from like elementary books. It's just the regular first passage. But now what happens? The way we deal with it, we write an indicator function. If the particles if the system is in the reactive state, the game is over, so this indicator function will get the value 0, and if not, it will get the value 1, and we continue from here. So now we are at 0, it means on the target, and in the non-reactive state. So while this is a classical quantity that we know how to compute, this random variable is actually a little bit more tricky. And the way we compute it is we identify again that this is actually a renewal moment. So I will write the renewal equation, but since it's a short talk, I don't think I have enough time to talk about it in detail. But essentially, we are asking, okay, once we arrive, did we switch on the target or not? If we did not switch on the target, we wait a certain time, then we come to this point, and we have to come back again, and again we ask the question, did we react or not? Is an indicator function, and this random variable here is IID, is independent and identically distributed as that one. So taking the mean of this renewal equation and the Laplace transform, we can get all the quantities that we want. So I will just show you the results, and we will not do it together. For the mean, so if I started at 0 in the non-reactive state, how much time it will take me to react in this gated reaction? And that is the equation, and I want you to notice two things. One is that on the left side we have the gated quantity, the mean reaction time. But on the right side, we only have the parameters of the problem and the first passage quantity. So on the right-hand side, we only have the ungated problems quantities, and that means that if I know to solve a simple first passage problem, I simply plug it in here, and I have already the result for the gated reaction. Another thing I want you to notice is that the notation might be tricky, but that is the mean of the first passage time, and that is the Laplace transform evaluated at the relaxation rate. So essentially the entire distribution of the first passage time is getting into play. It's not just the mean that affects, it's the entire distribution, and that means that fluctuations in the return time, they are all getting inside the mean of the reaction time. And so we'll do two checkups. One is we will take the limit of very fast relaxations, and if we will do it, if the system transitions very, very fast, we actually return back to the scenario of like geometrically distributed partial reactivity, what we have seen earlier on. This is simply the average time that you wait on the origin before you leave, and that is the time that it takes you to come back. So it's essentially the first return quantity, the mean first return time. And another thing that I will show you is what happens if you vary the fluctuations now in the return time, because we have seen that it's dependent on the entire distribution. So let us take a few distributions, all of them with the same mean, and just the only difference would be different fluctuations in the return time. And you can see how, so we quantify, maybe it's not known, the fluctuations by what is known the coefficient of variation, which is simply the ratio between the standard deviation and the mean. And as this quantity increases, you can see that the mean reaction time is getting larger. And actually the black curve here is simply deterministic case, so it's deterministic return time. Okay, but not always we have a finite mean. So in these cases, we can also take the Laplace transform of the PDF and get a similar, a little bit more complicated, but essentially a similar relation where you see that on the right-hand side, you only have quantities like the Laplace transform of the first passage, the regular first passage, the ungated first passage problem, and on the the left-hand side, you have the gated PDF. And we can, so it means that if you know how to solve a first passage, you can just plug it here, and again, you get the gated result very easily. And that is just a demonstration how to do it if you are considering CTRW on the 1D line. So we know how to get the first passage PDF, and simply by plugging it in the formula above, you get the solution, and it agrees perfectly with simulations. And also we can explore the general formula that we have and see general effects that happen to gated reactions. So we have general formulas. For example, we can see here that the asymptotics is inherited. Just the power law is changing, and we can determine exactly what would be the prefactor. Another interesting thing that we can see is that if you spend a lot of time in the non-reactive state, it's called the cryptic regime. So most of the time you're spending hidden. It's hard for you to find the target, or it's hard for you to react. You have a very, very long, over a few decades here, interim regime that has a completely different power law. So initially you can think even that you have different asymptotics, and we can exactly determine what would be this power law and what is the prefactor. And this kind of general calculation we are doing in this work and in other works. And finally, numerics. We have also shown that sometimes instead of it might be a difficult problem. If you don't know how to solve the problem analytically, you have a very large parameter space if you have to probe the entire alpha beta lines. So what you can do is just simulate the regular first passage process and plug it in the formula, and then you get complete agreement as if you have simulated the entire phase space. Yeah, these are the main things that I wanted to show. We have other works we have explored after that, discrete space and discrete time. A very new work that is now on arXiv is the continuous space and time analog, where we also consider entire volume like an interval that is now gated, that might have a lot of applications in biology and so on. And another application, another direction that we have recently uploaded to arXiv is the reverse problem, where we want to infer. All we know is the detection time, and we are trying to find the first passage time or the rates in which the system transition. So we also give a lot of motivation, where in reality, in experiment, there are cases where you can only measure the detection time. And these recent applications, you can also find them in a poster by engineer Kumar from Pune, our collaborator. And if you want, go talk to him, and he will explain even more. I have more time, I guess. Okay. Yeah.
Yeah, we have still a few minutes for questions.
Can you apply this to actual chemical reaction networks where the state space consists of sort of all the combinations of copy numbers?
Oh, the combination of copy numbers, that I'm not sure I understand. When you have multiple states.
So if you have a chemical reaction network, the state is specified by knowing all the copy numbers of each of the types of molecule present. And then a reaction, in principle, is also a walk on that network somehow. So would what you're doing work in that context?
That is a single particle.
You have a single particle that's representing the kind of state of the multi-particle system.
Yeah, we'll have to talk about it. Once you add averaging over multiple targets, the problem it's a little bit more complicated. It depends now where is the gate on, which particle is doing the gating, and
Okay.
but you can actually, so we have solved it for a two-state system, maybe some sort of a coarse-grained picture, but you can definitely solve it for a multiple-level system. The copy number, we should discuss it.
Okay, well, we can talk offline.
Yeah, sort of a related question. There have been a lot of experiments on single enzyme kinetics, you know, by who? Sunny Z, correct, by Sunny Z. And they look at the modification of the Michaelis-Menten kinetics coming from, you know, single stochasticity of particle encounters and state changes and so on. Have you, it will be okay to compare your, I mean, that might be a good experimental system to look at and compare your results with.
So the last project is actually a build-up for that. We are really, we wish to find the experimental system to finally show that it can be measured. Usually it's a problem to do it in the forward direction, but we hope that maybe in the inference problem we'll get some luck with experiments. The Michaelis-Menten is a different scheme and perhaps can be related to that. We have thought in this direction, but it has some more components, and this is like a little bit different than that. So I should also inquire about those experiments of Michaelis-Menten. But you're saying these are single particle.
Yeah. There were very nice experiments on this. And the other extension is to look at multi-state Markov process, which might be, let's say, three-state Markov process rather than a two, but which violates detailed balance, you know, and then there are lots of chemical reaction dynamics which are driven out of equilibrium. So
we have other motivations also to go beyond the two-state. Okay. This is just the simplest possibility. We wanted to cover that, but at least three states, there are many stuff that leads us to go in this direction as well. Yeah.
Okay. Thanks. If there is no more questions, I will thank you all for this nice talk. And the next talk is by Subhasri. The exact calculation of the probabilities of the rare events in cluster aggregation.
Yeah, sure. Good evening to all of you. So I'm Subhasri, and I would like to thank Arnab, Dr. Arnab and Dr. Pinaki for this opportunity to speak at this conference. So this is a work which has been done in collaboration. Okay, so this is a work that has been done in collaboration with my guide, Dr. R. Rajesh, and Dr. Zabronsky. So in the title, you can see there are two important things that we should notice. One is cluster aggregation, which is our system, and the other is rare events. So aggregation is an irreversible phenomenon, and it's present in many physical systems in one way or another. Biological systems, if you take protein clumping or blood coagulation, the first figure, I don't know. Okay, you can see the first figure is the blood coagulation, second one is the formation of clouds, third is protein clumping, etc. on the left hand side. And what is aggregation? So we take two masses and they collide and stick together to form a bigger mass. So if mass is m1 and m2 are colliding, they will form a bigger mass which has a mass m1 plus m2 with a certain rate which is proportional to what we are calling a collision kernel, and that is the k, which you can see on the schematic diagram. It's a function of the colliding masses. So the other part is rare events, right? So rare events we all know. Natural disasters is a very classic example of them. And of course, we understand that they are infrequent, but it is very important to study because, you know, it could happen at any time and it has a significant impact. The first schematic diagram is the rare event in aggregation itself, where some misfolded proteins clump together to form what are called plaques in the case of causing neurodegenerative diseases such as Parkinson's or Alzheimer's. This one is for Alzheimer's. Okay. So the model is as follows. We have m particles of mass 1 initially. This is our system, and there are some collisions occurring. After every collision, there are multiple configurations which are possible. So in this figure, you can see there are 4 collisions occurring, and after every collision, there are many configurations. And because of this, there are many trajectories. So what do I mean by trajectory? From the first collision to the last, that is the 4th collision, there is a path of arrows, right? So every such path is a trajectory, right? And all the information about the shape of the colliding clusters or area of cross section or all these things, even the transport information, everything we have contained in this collision kernel K, which is a function of the masses, colliding masses. And the total mass m is always going to be conserved after every step. Okay. Now the important thing is, why are we studying this? Aggregation has been studied for more than 100 years now. The first study was done by Smoluchowski, I guess, in 1917, and he gave a differential equation for the typical Nm. What is Nm? The number of particles of a mass m. So that is what was described. So with this, we can find out the typical mass distribution for very few kernel choices, for very few k. Right? Some examples are the constant, sum, and product kernel. These are the most common and classic kernels which have been solved and exactly. And there is a very palpable lack of results for atypical results or atypical events or rare events in cluster-cluster aggregation. Just an aside, I mean, when I was working on these slides, I remembered around more than 10 years ago in Chennai, during, I think, summer or monsoon season, whatever, it was raining. But it suddenly turned into a hailstorm. We were on the road and we saw this. This never ever happens in Chennai. This is really a rare event. And it actually involves aggregation also. There are models which have been proposed for raindrop formation which use aggregation. So it could be a very direct application of this. Okay, so the main question we are asking is this. So look at this plot here. It's a plot of the mean number of clusters. So what is N of t? N of t is the number of clusters which decay with time t, right? The red trajectory shows the typical way in which it decays. So I've marked on the y-axis, I've marked M, capital M and capital N. Capital M, as we said, is the initial number of monomers, which is just mass 1, which is M. And finally, the state is that whatever the configuration we may get, we are ending with n clusters. There will be a total of n clusters. That is what we want. So there are 2 conditions. Initial condition is that there are m particles of mass 1. Final condition is that there are n particles or n clusters. Clusters is a better word. There are n clusters. Now, with these 2 constraints, there could be many trajectories possible. So our question is to ask, what is the probability that some trajectory like this is atypical, right? So the quantity we are looking at specifically is P of m and t, which is the probability of n particles remaining at a time t, given our initial condition. And what is P of m and t for atypical times? That is, what is the probability of such an atypical trajectory is what we are asking. And the results are as follows. We find that there is a large deviation function. Okay, so the probability P of MNT basically decays exponentially in the limit of large M, large total mass in the system, right? And under the condition that phi, which is the fraction of particles remaining, is finite, and also the scale time capital T is finite. Under these conditions, for any collision kernel you will take, there exists a large deviation principle, and there is a rate function associated with this principle, which is given by f of phi comma t. So, of course, this leads to the natural expectation that f of phi comma t should be 0 at the typical point, typical t, right? Because that would mean that P of MNT is maximum, right? So that also we find is true from our results. This is also true for all kernels, Kij. Apart from this, we have usually in large deviation calculations, you could get the large deviation principle, but it is difficult to do that also. But even if you do that, solving it and getting the actual analytical form of the rate function, the f of phi comma t, is a little tricky. So, but we have managed to get it for the 3 classical cases, as I said, constant, sum, and product kernels. And these are the results. So the first, from left to right, it's constant, sum, and product kernels. And I've plotted f of phi comma t with respect to t. This t that I'm talking about is scaled time. And I've plotted it for different phis, 5.3, 0.5, and 0.5, yeah, and 0.8. And shown, the last line just shows the actual exact answers for each of these kernels. As we can see, at the typical time, this f of phi comma t goes to 0. We also find that the number of clusters decays. I mean, we find in principle first order differential equation for the decay of the number of clusters for any kernel again. Again, this can be solved exactly for the constant, sum, and product kernels. This E is a parameter which, if E is 0, you would recover the typical case. And E could be positive or negative, and that would take you to either sides of the typical trajectory, you know, long time or short time. So these are the, so we are calling this instant on trajectory because of the way the calculation goes. I'm not going into that. But so these are the trajectories. The middle blue line shows in each plot, the blue line shows the typical trajectory, and the red and violet show the atypical trajectories. This is to check our results and make sure they're fine. We also developed an algorithm to access these atypical trajectories. This algorithm involves 2 moves. The first move is that I choose a certain collision and choose a certain configuration and then just alter it so that none of the other configurations in the trajectory changes. Right? So the trajectory is essentially changed only at a certain point, slightly perturbing the trajectory is what I'm doing. So it looks like this to visualize it. And the next move is that I choose a certain collision and change the waiting time. So, but this, in this case, since the waiting time changes, the total time taken for m minus n collisions would also change. That would also change. So this is how it looks. Yeah, we have checked that this algorithm is ergodic, and the results are here. We benchmarked it with the constant kernel because the constant kernel is the simplest case possible, right? Because in the constant kernel, k of ij is just 1. It doesn't depend on the colliding masses. So it is kind of easy to solve by hand. So we got P of MNT for that and benchmarked it with our simulation results also. And we find that this measures very low probabilities of 10 to the power minus 40, sometimes 60, depends. Sorry, so I would just like to go back and just point out something here. So, yeah, in this slide, so this is the, as I'll remind you, this is just the large deviation function for the constant, sum, and product kernels, and there are some expressions at the bottom. These expressions also very nicely give the asymptotic answers, as in the long time answers as well as the short time answers. So an interesting fact that you can note is that at the short time, for all 3 kernels, f of phi t just goes as 1 minus phi into ln t. That's what it is for all three kernels. It just has a power law behavior with an exponent 1 minus phi. And of course, the long time behavior differs. That is there. Okay. Okay, so this is just a brief slide about the method of solution that we have. So we wrote a master equation for this quantity P of vector n comma t, which is just the probability of a certain configuration n in time t. And from there, we could write P of m n t, which is our quantity of interest, in terms of this P of n comma t. And rewriting it in a Schrodinger-like form, which has a Hamiltonian-like term coming in, we could exponentiate it and find, write it in a path integral form so that we could extract an action out of it. That action, after some algebra, etc., becomes the rate function. And some scaling also, then it becomes a rate function. Okay. So to summarize, we have basically developed an analytical formalism and a numerical method to study the tails of P of m and t, and we find that they match up very well. The large deviation function, in principle, is there for arbitrary kernels, but it can be solved for the classical cases of constant sum and product, exactly. And we see that another check is that the Smoleshowski result is recovered at the typical time, which also we find to be true. And the equation for the instant on trajectory for any kernel is an icing on the cake, which again, and there could be many directions in which this could be taken. One is to, again, obviously to study, use this formalism for other kernels, other collision kernels. We might need to do some approximations and some numerical magic, but yeah, it might be possible. And then aggregation fragmentation process is also possible because it just involves one more term in the master equation. Maybe that could be possible. And instead of, and here we have not included, we have not explicitly spoken about any transport process. We just said that everything is contained in the kernel. We could try diffusive aggregation also, since that's a huge branch of aggregation. And instead of binary aggregation, we could go for k-nary aggregation and see if we can get some scaling loss there, whether a large deviation principle is available there also. Because one important thing that should be noticed here is, in many theoretical papers on aggregation, the form of the kernel which is taken is always homogeneous. Mostly, as far as to the best of my knowledge. But when we do the calculation, it doesn't, that form doesn't come in anywhere. We just keep it as Kij and we get some large deviation result. So whether that will, at some point, the homogeneity will affect the solution at some point is something to think about. So, thank you.
So you have, yeah, Jeremy, yes. Yeah, you go ahead. Yes.
Thank you for this very interesting talk. So maybe I missed something. So what are exactly the settings that you're putting in your aggregation process? Can you repeat? What are the settings that you're considering in your aggregation process? Or in other words, settings. Yes. Okay. Or in other words, so basically, what are the source of fluctuations in your large deviations?
Settings as in.
No, so basically, are you considering a solution, directly a solution to the Smoleshowski equation?
So the Smoleshowski equation is recovered from this formalism. So we get an action, and at the typical point, we recover the Smoleshowski. When we minimize the action to find the Euler-Lagrange equations, etc., we end up with the Smoleshowski equation at the typical time.
But this is just a mean field equation for the average, in principle.
Yeah.
So what is the source of fluctuation compared to this Smoleshowski equation that is giving the large deviations? It's a number of fluctuation. Okay, so it's a finite number. Okay.
Clusters as well as the trajectory, since this E is the parameter which controls what trajectory we look at. So depending on the value of E, we can get very, very rare trajectories and make them typical in some sense.
And then, so what you assume, I guess, is some kind of well-mixing
Yes, we do.
condition
Yeah.
that certainly you will lose when you are talking about non-homogeneous things.
Ah, right, yeah.
Yes.
Oh, thanks.
Yes.
So I was wondering whether you could extend that and constrain not just a overall number of clusters, but a sort of scaled version of the cluster size distribution, because then you could also get typical cluster size distributions.
Yeah,
direct
actually we
distributions,
can.
etc.
That's another ongoing work.
Okay.
We can get the cluster size distribution. So I didn't show you the entire calculation, but the Zi bar and Zi, which is there in the last line, right? They are such that the Zi into Zi bar is Ni. That is your mass distribution. So we have also, for the constant sum and product kernels at least, we have got exact expressions for both Zi and Zi bar. Just multiplying them would give the mass distribution. We have to check it and other things, but we have, it's ongoing work, yeah.
But what I was asking is whether you could constrain that, right? So here you're extracting the most likely cluster size distribution for a given phi, but you could maybe also constrain that, because then you can get your results by contraction, basically, right? And often putting more constraints in makes the calculation simpler. So,
yeah.
Sorry, in this in the action, where does the Kij come in?
Kij comes only in the E.
E, I see. And your m going to infinity limit goes through capital T.
Yeah, yeah.
Okay.
Yeah.
So you take the saddle point there and something. Okay.
Yes.
Sorry, what makes those three cases exactly solvable?
So just the form of the kernel. So the constant kernel was Kij is 1. The sum kernel is Ki. So the thing is, the rate of collision of mass I and j would actually be Kij into Ni into Nj, which is number of I and number of j. So what happens is that when you sum over, it either gives the number of clusters, total number of clusters, or the total mass, which makes it easier. Whereas if you had some I square or something, you would get the second moment of the number distribution. So you would get higher and higher moments, which is kind of hard to solve. We need to look for other methods. So, but these three cases are easily solvable.
Yeah, one more question from Arnab.
Yeah, Shubhasri, I was wondering, like in this case, right? So I understand the typical fluctuations in the large deviation. What would be the most atypical behavior? I mean, I'm trying to understand. It's like just one single cluster.
So no, we in our problem we have defined two constraints, right? So we start with m particles and end with n clusters. N is not equal to 1, because that's a totally different ballgame. It leads to gelation, right, etc. So n not equal to 1. So in this, probably the most unlikely cluster could be the leftmost or rightmost path here. The rightmost, I would say, because there the one collides with the highest mass in each. 1 plus 1, 2, and then the next arrow is 2 plus 1, 3, next is 3 plus 1, 4. That kind of thing happens. That could be the most unlikely path, but I don't know. We could check that, of course. That can be done.
See that the rate function?
Yeah. Yeah, we can see that. Yeah. In fact, yeah, I would say that it is rare, because when we try to asymptotically calculate for the product kernel or sum kernel, right? This is the trajectory path that we assumed in our calculations. It was we guessed somehow, and that gives the right asymptotic answer also. So at large times, that is the rarest configuration. That is, it coincides with the large deviation function, so that is pretty rare.
If there is no more question, let's thank Shubhasri for this nice talk.
Thank you.
We conclude the session. Pinaki has some announcement.
Yeah, no, not much of announcements. Thanks to all the speakers for very nice presentations. Thanks to the chair for doing an efficient job, excellent job. So that's the end of the first day. Now we have a high tea plus posters, so mingle around and look at the posters. Dinner, for those of you around, is on the upstairs of the canteen, and please have your badge on. Sorry to remind you about that. Yeah, and then we see you tomorrow morning. Thank you.